In section 031, we were calculating the derivative using the limit definition of the derivative. And in this section, we're going to learn a couple of shortcut rules. Some of them we actually learned already or saw already in 031. So we'll start just by listing the ones we're going to look at. Okay, so first we have the derivative of a constant is 0. Okay, we saw that previously, and that's intuitive because a constant function is a horizontal line, slope 0, and the derivative is a slope function, so that makes sense. Okay, and similarly, the derivative of mx plus b, where m and b are constants, that's the derivative of a line with slope m. So we saw in the previous lecture, or in 031, that this was equal to the slope m. Again, this makes sense because a line has slope m and the derivative is a slope function. Okay, here's another rule. If we have the sum of two functions, then the derivative is the derivative of f plus the derivative of g. Now this is easy to see from the limit definition of the derivative. Alright, so I'm just going to write it out. So I'll write PF for proof. Okay, we'll just sketch the proof. Okay, so what we want to do is take the derivative of a sum of two functions, and we're just going to stick this into the limit definition. Limit h goes to 0. Now our function is f plus g, so substituting in x plus h, we have f of x plus h plus g of x plus h minus the sum f of x plus g of x. And this could be split up into two limits. Alright, so we'll just grab the f of x plus h minus f of x over h. And plus grab the g's. That's because the limit of a sum can be broken up into the sum of the two limits. So there we have the derivative of f plus the derivative of g. Okay. And in a similar way, you can easily show from the limit definition the second to last limit rule, number 4, which is also a very simple one. If you have c as a constant, if you have a constant in front of the function, you can just pull that out in front. It's c times the derivative of the function. Okay. And again, this can easily be shown using the limit definition. The constant just pulls out in front. Now the last is the one that we're going to concentrate on. This is called the power rule. And this is a nice shortcut that we use a lot. All right, and we'll prove this for some functions. All right, this is derivative with respect to x of x to the power n is equal to n times x to the power n minus 1. And we'll prove this for n being a positive integer. But this is actually true where n is any real number. positive, negative, it can be fraction, rational, irrational, and is any real number. So this is the power rule. Let's just see, it's very, very easy to apply. We'll look at a little example. Let's say y is equal to x to the 10th. Then the derivative, we can simply write that as y prime, is equal to, bring the 10 down in front, and subtract 1 from the exponent, 10 minus 1, so we have a 9 here. So that's it, that's the derivative. If we were to do this using the limit definition, it would be very complicated because we would have to expand x plus h in parentheses to the power 10. Okay, so let's look at the proof of the power rule. The proof of the power rule for n, an integer greater than or equal to 1. Okay. All right, so actually we'll make it greater than or equal to 2 because for n equal 1 we already have the derivative of a line. Okay, so we'll do it for n greater than or equal, for integer n greater than or equal to 2. All right. So here, this will be the proof, and like I said, this theorem is true for all values, but we'll only look at the proof for integers. Now, first, what we're going to do is we'll look at n equal 3. Okay, so we'll start with n equal 3. All right, so let's suppose that we say y is equal to x cubed, and we want to know what y prime is. We're going to apply the limit definition, because that's all we have now, until we prove this little power rule. That's all we have is the limit definition. Okay, so we have substitute in to our function x plus h. So here we have, sorry, here's our function, substitute in for x plus h, so we have x plus h cubed minus our function. Okay, so that's the limit definition. Now all we have to do is expand x plus h cubed, and that's not difficult to do. Just multiply it out 3 times, x plus h times x plus h times x plus h. I'm going to just write out what it is, so I'll just leave it to you to actually expand it out. Right. So this is what x plus h times x plus h times x plus h is equal to. It starts with x cubed plus 3h x squared plus 3h squared x plus h cubed. Okay. So that's our x plus h cubed. That's all that. Minus x cubed. Let's rewrite this. First of all, we're going to cancel the x cubed and the minus x cubed. All right, so this is limit h goes to 0. Okay, these cancel, so I'm just left with these terms. All right, so I'm going to write the 3hx squared first, and here I'm going to factor out h squared. So we have h squared, and in parentheses we're left with 3x plus h squared. Okay. All right, so divide by h, so we have the limit as h goes to 0. Here we have 3x squared plus h into h squared, we have an h, and then we have this. Now take the limit as h goes to 0. Okay, so only this term remains. Here h is going to 0, so this whole thing, because it has the h in front, this goes to 0, and we're left with 3x squared. And that's what we expected from the power rule. When we took the derivative of x cubed, the 3 came down, we subtracted 1 from the exponent, and we got 3x squared like we expected. All right, okay, now for y equal x to the n. All right, so we have y prime is equal to limit h goes to 0, x plus h to the n minus x to the n, just using the limit definition, over h. Now here, expanding this, well, we have a rule called the binomial expansion rule, which we could use to expand that. So I'm going to use part of the binomial expansion rule. Just how it begins. It begins like this. It begins with x to the n, and then the second term is n, and then we have an h and x to the n minus 1. Okay. And then the rest of the terms start, the next term has an h squared in it, the next term has an h cubed, all the way up to h to the n. So in other words, the powers of h keep on increasing and the powers of x keep on decreasing. But the main thing is that the power of h keeps on increasing. So each term has at least h squared. The next term has h squared, the next term has h cubed. So we could factor h squared out from all the terms. All right, so that's what, doesn't matter what's left, but this is the rest of the terms with h squared factored out. Okay, then we have this minus, so that's our x plus h to the n in the simplified form, which is all we need. Now let's go back to the x cubed example. You see, this would have been the what I wrote for an asterisk. Okay, we had 3h x squared, that's our first term, plus h squared times the rest. This was the asterisk. Okay. So that's the asterisk for the rest. See, actually here. All right, now we cancel out the x to the n. Okay, and now divide by h. Okay, so here the first dividing by h, here we have n, x to the n minus 1, plus h times the rest. And now we're ready to take the limit as h goes to 0. So this is going to go to 0 because of that little h in front. And we're left with n x to the n minus 1. Okay, I'm just going to write that this comes from the binomial expansion formula. Okay, so now we're ready to use the power rule together with the other rules that we had above. All right, we'll see how we combine them in a minute. So let's start with a very simple example. Let's say y is equal to x to the 100. So y prime, bring down the 100 and subtract 1 from the exponent. Now we can have negative exponents as well. Okay, so here, or any real number really, bring down the minus 10. Minus 10 minus 1 is minus 11. Okay, let's say we have y equal x squared divided by x to the 10th. Well, in order to use the power rule, we need a single power. We can't have a quotient of 2 powers. So what we have to do is modify this, just subtract 2 minus 10. That's x to the minus 8. And now once it's in this form, in the form of a power, we're ready to apply our power rule and take the derivative. So bring down the minus 8 and subtract 1 from the exponent. Minus 8 minus 1, we have minus 9. So far we've been using integer exponents. We don't necessarily have to do that. Let's say we have y equals square root x. Rewrite this in terms of a power, that's x to the 1/2. Now take the derivative, the 1/2 comes in front. And here we have 1/2 minus 1, that's minus 1/2. Alright, we can rewrite this. That's 1/2 times 1 over x to the 1/2 of 1 over square root x. So let's write it as 1 over 2 square root of x. Okay, so that's the derivative of square root x. All right, now we're ready to start combining the power rule with other rules. All right, let's just scroll back to the other rules that we're going to use. Just 2 rules, these 2. Okay, these 2 here, that the fact that the derivative of a sum is the derivative of the first plus the derivative of the second, and also derivative of a constant, we can just pull the constant out in front. Okay, so in our next example we'll have y equal to a polynomial, let's say 10x cubed minus 3x squared plus 5x minus 2. So we're going to take the derivative term by term. Okay, that comes from the rule that the derivative of a sum can be done term by term, so we'll do that. And the constants will just stay out in front. So here y prime is equal to, we have 10, bring the 3 down. Okay, so we have 10 times 3x, subtract 1 from the exponent, x squared. Here bring the 2 down, 3 times 2. Usually we'll multiply these right away. X to the 1, subtracting 1. Derivative of a linear function is just the constant in front. Derivative of 5x is just 5. And the derivative of a constant is 0. So usually we would multiply, while we bring the 3 down, we would multiply it by 10 and we'd write 30 right away. And here when we bring down the 2, we'd multiply it by this 3 and we'd write minus 6x plus 5. So we see now we can take the derivative of any polynomial using our power rule combined with those other first 2 rules. Okay, just 2 more important examples. Let's say we have y equal x cubed plus x to the 5th over x squared. Okay. We have a single term in the denominator. When we have a single term in the denominator, we could divide to get a sum of powers. Divide the single term into the first and the second and get a sum of powers. So rewrite in the form where we can use the power rules. So divide x cubed divided by x squared is x. X to the 5th divided by x squared is x cubed. And now we're ready to take the derivative. Derivative of a linear is the constant in front, so the derivative of x is 1. And here we do the power rule, bring down the 3, subtract from the exponent. And let's do another one like this, just a little more complicated. Let's say we have y equal 5x to the 7th minus 2x plus 4. And this time we'll divide by the square root of x. Okay, we're going to do the same thing we did above. Remember, the square root of x is x to the 1/2. So we're going to divide x to the 1/2 into each term. Let's rewrite our function. Sorry, that's not y prime, but y. We'll start with y, rewriting our function. So we still have y equal to 5. X to the 7. 7 is 14 divided by 2. 14 divided by 2 minus 1/2. That would be x to the 13 divided by 2. Here's x to the 2/2 minus x to the divided by x to the 1/2. So 2/2 minus 1/2 is 1/2. And now this x to the 1/2 in the denominator, just bring it up. When we bring it up to the numerator, it's x to the minus 1/2. Okay, so now we've written y as a sum of powers, and we're ready to take the derivative. Bring down the 13/2. So we have 5 times 13/2, that's 75/2. Sorry, 65/2. Let me rewrite that. X to the, and now 13/2 minus 2/2, that would be 11/2. 2 times 1/2 is 2/2, or 1. So we don't have to write that. And here we have x to the 1/2 minus 1. That would be minus 1/2. 4 times minus 1/2, that's minus 2. X to the minus 1/2 minus 1, that's minus 1/2 minus 2/2, that's minus 3/2. And that's it. That's the derivative. We just leave it at that. So we're going to do one last example. Okay, so find the this is find the equation of the tangent line to y equal x cubed minus 3x squared plus 4 at point x equal 1. So for the equation of the tangent line, the first thing we have to find is the slope. Let's say we call this f of x. Just the function notation will be useful here. The slope will be the derivative at 1. So first let's find f prime of x. Just find the derivative. Okay, power rule, 3x squared minus 6x, and the derivative of a constant is 0. Okay, so f prime, now plug in the 1. That's 3 minus 6, or minus 3. All right, now we want to know, what about a point? For the equation of a line, we need a slope, and we need the point. So the point is going to be, well, we have x equal 1. Let me put 1 here. It's going to be 1, comma, f of 1. All right, so what's that? That's 1, comma, just substitute in 1 here. We have 1 minus 3 plus 4. So that's 1, comma, 2. 1 minus 3 plus 4, that's 2. So that's our point. Okay. So for our slope, we have minus 3. And for our point, we have 1, comma, 2. All right, we can use the equation of the line. Y minus y0 equal m. X minus x0. All right, so we have y minus 2, the y coordinate of our point, equal m. Our slope is minus 3. This is our m. This is our x0, y0. So y minus y0 equals m, x minus 1. And you could put this in the form y equal mx plus b if you like by opening up parentheses. But I'm going to leave it at that.